Hi everyone. All right, in today's lesson, we're going to talk about how to analyze motion graphs. Right. So, if you remember in our last lesson, we were looking at the constant velocity cars. You guys were measuring how fast they were, right? And we were talking about speed, right? Talking about how fast they're going. You guys collected that time and distance data, and then you graphed it, or at least you're supposed to graph it. So, we're going to go through today's lesson, and then if you have time, you can go back and kind of figure out how to graph that data and determine the velocity of that constant velocity car. All right, so first things first, we had a graph here. I want you guys to take a second, you can pause the video and figure out which of these runners is fastest. All right, we're going to continue. If we look, we see three different runners. They all run the same distance, right? They all reach the same distance marker, right? Let's say this is your 100-meter dash, right? Or 100-meter sprints, or even the 1 mile run. So each runner, we'll just call it a mile, right? Each runner has now run 1 mile. The question is, who ran that 1 mile the fastest? Or who did it in the least amount of time? All right, if we look at each of these lines here, we can see runner A, right, finished at whatever time this would be. Runner B finished at whatever time this would be. And runner C finished at whatever time this would be. So if you're looking at all this information, it should be pretty clear that runner A is the fastest. They ran that distance, the same distance as runner B and runner C, but in the least amount of time. But what if our graph is showing a velocity versus time on the X and Y? Right? So you think about velocity. Velocity is kind of like speed, right? Showing how fast each runner is going. If you notice, these lines are different than the lines in this graph. In this graph, we have a linear pattern for each runner, right? Every second or every unit of time, the distance is increasing at the same rate. In this case, we have a horizontal pattern. Right? So thinking about if down here, this is a velocity of 0, and just to keep this simple, let's say this is a velocity of 100, right? Which runner is moving the fastest? You can pause the video. All right. Now in this case, runner 1 is also the fastest. All right. So again, we can say each runner, let's say this is running 30 miles per hour, or I guess meters per second. That's still really fast. Whatever. This is 60. This is 90. Right. Not really realistic numbers if you think about meters per second. But in any case, runner 1 would clearly be moving the fastest. Because it's a horizontal line, that's also showing that they're not getting faster or slower as they're running. They're maintaining that same speed. Now, most of you guys will interact with speed when you guys begin driving a car. Most of you guys should know what this is called, right? This is what you use to determine how fast your car is moving. You want to kind of keep an eye on your speed so that you are going at a safe speed within the speed limit of wherever you're driving. Now, you can talk about it with others and pause to figure out what this is called. Okay. We call this a speedometer, and it's spelled speed O meter. Right? Obviously, you can take out the hyphens, but it's called a speedometer, right? It's basically speed per meter, right? Or speedometer. Now, you'll notice if you look at any speedometer of a car made in the United States, it has 2 sets of numbers, right? 2 scales, right? Each one has a different unit. Now, these units matter, okay? First things first, what I want you guys to do is pause the video and then answer questions 1, 2, and 3. You can unpause it once you've answered those. All right. For question 2, right, it's asking what is the speed shown in this speedometer. So you notice this dial here is actually covering 2 different numbers. So they're going approximately 55 miles per hour and approximately 90 kilometers per hour. Now, depending on where you're driving, if you drive up into Canada, for example, you'll be using a different unit for speed. Now, there's no good scientific reason for this. This is just based on the type of units that each country has adopted, with the US being one of the very few countries that uses the imperial system, which is going to be inches, feet, yards, miles, Fahrenheit. All right. So, the units matter. If you're driving 55 miles per hour in the United States, that's pretty fast. But if you're driving 55 kilometers per hour, right, that's not particularly fast, right, depending on where you're driving. Fast for a neighborhood, but not fast for a highway. Now, when we're talking about finding the speed of an object, what we want to do is we know that our units for speed are going to be our distance, right? In this case, you see 2 examples, miles and kilometers, divided by time. In this case, both are measured against hours. So here we see that we have distance and time on our graph. So if we divide distance and time, what we're essentially doing is we're just finding the slope of a line. So looking at this line here, we see that we have a change in distance and a change in time. All right? We call this a rise and a run. If you remember from middle school math, finding the slope of any line, you take your change in the y, or the rise, and you divide it by the change in the x, or the run. In this case, what's rising or increasing is our distance. What's running or increasing the x is the time. Right. Now, if we put this into numbers, we can see that we've increased from a distance of 0 to a distance of 100, right? So there's been a change in distance of 100 meters. And a change in time from 0 to 10 seconds. So what we're going to do here is we're going to do a little bit of math, right? To find our slope, we're dividing the rise over run, which is the distance over time, which in this case is going to be 100 divided by 10, which is just going to give us 10. But you notice we're not only dividing the numbers, we're also dividing the units. Right? Now in this case, we can't really do anything with meters divided by seconds, so we leave it. All right? Meters divided by seconds. Alternatively, we could write this as 10 m/s. Same thing. Alternatively, we could write this as 10 mps, meters per second. All right, that's kind of what you see here in your speedometer. Instead of seeing a fraction, right? I guess you see a fraction for kilometers per hour. Instead of seeing a fraction for miles per hour, right? It's just mph. The per is just a stand-in for the fraction or division sign. All right. So to sum up, if you want to find how fast something's moving or their velocity, our formula is simply going to be velocity equals distance divided by time. Now we don't necessarily need to write this whole formula out each time. we can actually use some symbols to represent each of these. So a V for velocity, a D for time, or a D for distance, and a T for time. So what you guys should try to do is try to find, all right, what is the distance divided by time for this graph, right? Or how fast is this object moving? All right. So what's the change in distance? You can pause to try and solve this. Actually, I'll give an answer key to the sub so that they can go ahead and show you guys if you want to check your work. All right, next. About 2 weeks ago, I think at the beginning of October or the end of September, the world record for the marathon race was actually broken. It stood for a few years and it was recently broken. So again, a marathon is a pretty long distance run. It is 26.2 miles. And the runner who won this, Kelvin Kiptum, ran it in 2.01 hours, or about 2 hours and 35 seconds. So once again, using your formula, figure out what was his velocity. All right, you can check your answer with today's sub. All right, moving on. Looking at two cars here. All right, we have two cars that are moving at different speeds. We have what's called a motion map here. All right. A motion map is essentially like if you took a camera and you set it up in one spot, and then every second you took a picture, you could see the change in position of your object at each second. So we have this done for two different cars. You'll notice that the scale here is the same for both, right? They start at 0 and they go to about the 10-meter mark, right? So look at the difference here. Look at the spacing. Look at where they are at each second. What I want you guys to do is try and figure out what would the speed of each car look like on a distance time graph, right? So this is kind of going back to this very beginning here, right? Right, instead of 3 lines, right, you just have 2, right? One for each car, a red line and a blue line. The question is, which line is going to be steeper, right? If you have your red line representing the red car and a blue line, they both go the same distance. The question is, which one reaches that distance first? So which one's going to be steeper? That's for you guys to try and solve here. Same thing with the velocity. You'll notice that they're evenly spaced out, meaning they're not getting faster after every second. They're not getting slower after every second. They're moving approximately the same speed. So just like our velocity graph at the very beginning, we should draw two horizontal patterns. And same thing, right? Where is our blue line going to be? Is it going to be on top, or is it going to be on bottom relative to the red car? All right. Lastly, a couple challenge questions here. I'll have you guys do this on your own. Just kind of explain it. So Usain Bolt, right, famous sprinter. He ran the 100-meter run, which is kind of the short distance run in the Olympics. He set the world record in 2012 by running the 100 meters in 9.63 seconds. This was significantly faster than the gold medalist from 1896, who ran that same race in about 12 seconds. Right? So in theory, let's say we put those two runners up against each other, both at their primes. Right? They're both running the same distance, 100 meters. Usain Bolt wins that race in 9.63 seconds. The runner from 1896 is still running, right? He's behind. It's going to take him another few seconds to reach that finish line. The question is, how far behind are they when Usain Bolt is crossing the finish line? So think about how you could graph this. And how can you use that graph to help you determine how far back was that runner. Okay, to kind of wrap up this activity, one, we have a couple position time graphs. These are also known as distance time graphs. See if you can convert this graph into a velocity time graph. Same thing here. The difference in this one is you'll notice that there's a change in speed. So what might that look like? For those of you guys who are just flying through this, I have kind of an activity that brings this all together here. There's a little QR code. It's an online activity. You can do this on any device. Go ahead, scan that, and that should take you to the end of our class time.